calculate balancing neutral loads, follow these steps. Firstly, determine the total load. Calculate the sum of all the loads connected to each phase. For example, if phase A has 5 kilowatts, phase B is 6 kilowatts, and phase C is 4 kilowatts, the total load is 15 kilowatts. Secondly, distribute the load evenly. Divide the total load by 3 to obtain the average load per phase. In this example, the average load is 15 kilowatts divided by 3, which equals 5 kilowatts. Thirdly, calculate the neutral current. The neutral current is the vector sum of the currents in the three phases. Since the loads are balanced, the currents in each phase will be equal. Therefore, the neutral current is 3 times the average load current. In this example, let us assume a 240 volt system, then the neutral current is 5 kilowatts divided by 240 volts, which approximately equals 20.83 amps. Fourthly, verify the balance. The neutral current should be approximately 0 for a balanced load. If the neutral current is not close to 0, there is an imbalance in the load. Fifthly, adjust the loads. If the load is not balanced, adjust the loads on each phase until the neutral current is minimized. This can be done by moving loads from one phase to another or by changing the power factor of the loads. Now let's review some examples. In the first example, we will use the following values. Phase A is at 5 kilowatts, phase B is at 6 kilowatts, and phase C is at 4 kilowatts. The total load, therefore, is 15 kilowatts. The average load across all phases is 5 kilowatts, and the neutral current, as shown earlier, at 240 volts would be about 20.83 amps. Here is another example. Phase A is at 6 kilowatts, phase B is at 5 kilowatts, and phase C is at 4 kilowatts. The total load is 15 kilowatts. The average load is 5 kilowatts, but the neutral current would be 10.42 amps, indicating an imbalanced system. For a balanced three-phase load, the power factor should be the same on all three phases. If the load is unbalanced, the voltage drop across the neutral conductor may be significant, which can cause safety hazards. It is recommended to use a load calculator or software to ensure proper load balancing. To elaborate further on balancing neutral loads, let's consider the underlying principles and practical implications. Neutral current arises in three-phase power systems when the loads on each phase are not equal. In a perfectly balanced system, the currents in each phase are equal in magnitude and 120 degrees apart in phase angle. The vector sum of these currents is zero, resulting in no current flowing through the neutral conductor. However, in reality, loads are rarely perfectly balanced. This imbalance leads to a non-zero neutral current, which can have several consequences. Firstly, increased energy losses. Neutral current contributes to resistive losses in the neutral conductor, wasting energy and increasing operating costs. Secondly, voltage drops. Excessive neutral current can cause voltage drops along the neutral conductor, leading to voltage imbalances at the load end. This can affect the performance and lifespan of sensitive equipment. Thirdly, overheating and fire hazards. High neutral currents can cause overheating of the neutral conductor, potentially leading to insulation breakdown and fire hazards. Fourthly, nuisance tripping. In some cases, excessive neutral current can trigger ground fault circuit interrupters or other protective devices, causing unnecessary downtime. To minimize neutral current and its associated problems, it is essential to balance the loads across the three phases as much as possible. This can be achieved by strategically distributing loads among the phases, taking into account their power consumption and power factor. In practice, achieving perfect balance is often difficult, but even small improvements can significantly reduce neutral current. Several techniques can be used to balance neutral loads effectively. 1. Load monitoring. Regularly monitor the current in each phase and the neutral conductor to identify imbalances. 2. Load shifting. Move loads from heavily loaded phases to lightly loaded phases to equalize the current distribution. 3. Power factor correction. Improve the power factor of inductive loads, such as motors and transformers, to reduce reactive power and improve overall load balance. 4. Dedicated circuits. Use dedicated circuits for large, unbalanced loads to prevent them from affecting the overall system balance. 5. Neutral conductor sizing. Ensure that the neutral conductor is adequately sized to handle the expected neutral current without overheating. 6. Harmonic mitigation. Address harmonic currents, which can exacerbate neutral current problems, by using harmonic filters or other mitigation techniques. To further illustrate the concept of balancing neutral loads, consider a practical example. Suppose a small commercial building has the following loads connected to a 208/120 volt 3-phase 4-wire system. Phase A has 20 amps of lighting, 15 amps of receptacles, and 10 amps of a small motor. Phase B has 18 amps of lighting, 12 amps of receptacles, and 8 amps of a heater. Phase C has 22 amps of lighting, 10 amps of receptacles, and 5 amps of a computer. To determine the neutral current, we need to calculate the current in each phase considering the 120 volt line to neutral voltage. The current due to lighting in phase is 20 amps, in phase B it is 18 amps, and in phase C it is 22 amps. The current due to receptacles in phase A is 15 amps, in phase B it is 12 amps, and in phase C it is 10 amps. The current due to the motor in phase A is 10 amps. The current due to the heater in phase B is 8 amps. The current due to the computer in phase C is 5 amps. The total current in phase A is 20 amps plus 15 amps plus 10 amps, which equals 45 amps. The total current in phase B is 18 amps plus 12 amps plus 8 amps, which equals 38 amps. The total current in phase C is 22 amps plus 10 amps plus 5 amps, which equals 37 amps. The neutral current is the vector sum of the currents in the three phases. Since the phase angles are 120 degrees apart, we need to use vector addition to calculate the neutral current. This calculation can be simplified by using a phasor diagram or specialized software. However, for a rough estimate, we can approximate the neutral current as the arithmetic difference between the largest phase current and the sum of the other two phase currents. In this case, the largest phase current is 45 amps in phase A. The sum of the other two phase currents is 38 amps plus 37 amps, which equals 75 amps. The difference is 75 amps minus 45 amps, which equals 30 amps. Therefore, the approximate neutral current is 30 amps. This indicates that the load is significantly unbalanced. To reduce the neutral current, we can shift some of the loads from phase A to phase B or phase C. For example, we could move 5 amps of lighting from phase A to phase B. This would reduce the current in phase A to 40 amps and increase the current in phase B to 43 amps. The new neutral current would be approximately 43 amps plus 37 amps minus 40 amps, which equals 40 amps. This is a slight improvement, but further adjustments may be needed to achieve a more balanced load. It is also important to consider the power factor of the loads. Inductive loads, such as motors and transformers, have a lagging power factor, which means that the current lags behind the voltage. This can contribute to neutral current problems. To improve the power factor, we can use power factor correction capacitors. These capacitors provide reactive power that offsets the reactive power of the inductive loads, bringing the power factor closer to unity. Power factor correction can significantly reduce neutral current and improve overall system efficiency. In addition to load balancing and power factor correction, harmonic mitigation is another important aspect of neutral current management. Harmonic currents are non-sinusoidal currents that are generated by nonlinear loads such as electronic devices, variable frequency drives, and LED lighting. These harmonic currents can flow through the neutral conductor and exacerbate neutral current problems. To mitigate harmonic currents, we can use harmonic filters. These filters are designed to block or reduce the flow of harmonic currents, preventing them from reaching the neutral conductor. Harmonic filters can be installed at individual loads or at the main service entrance. Another approach to harmonic mitigation is to use phase-shifted transformers. These transformers are designed to cancel out certain harmonic currents, reducing their impact on the neutral conductor. In summary, balancing neutral loads is essential for minimizing energy losses, preventing voltage drops, avoiding overheating, and ensuring reliable operation of electrical systems. By carefully distributing loads among the phases, improving power factor, and mitigating harmonic currents, we can significantly reduce neutral current and improve overall system performance. Regular monitoring, load shifting, and the use of appropriate mitigation techniques are key to maintaining a balanced and efficient electrical system. Furthermore, adherence to electrical codes and standards is crucial for safe and effective neutral current management. The National Electrical Code, or NEC, provides guidelines for neutral conductor sizing, grounding, and bonding, which are essential for preventing electrical hazards and ensuring proper system operation. The NEC also specifies requirements for harmonic mitigation in certain applications. It is important to consult the NEC and other relevant standards to ensure compliance and safety. In addition to the NEC, other organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC, develop standards and guidelines for power quality and harmonic mitigation. These standards provide valuable information on best practices for neutral current management. It is also important to consider the specific characteristics of the electrical system and the loads connected to it when designing and implementing neutral current management strategies. Factors such as the system voltage, the load types, and the operating environment can all influence the effectiveness of different mitigation techniques. A thorough understanding of these factors is essential for developing a customized and effective solution. In conclusion, balancing neutral loads is a multifaceted issue that requires a comprehensive approach. By combining load balancing, power factor correction, harmonic mitigation, and adherence to electrical codes and standards, we can create a safer, more efficient, and more reliable electrical system.